Hi, Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. So now we will go for the new topic, which is optimization. And this topic basically have three subtopics. First is the linear programming, and then the graphical solutions, and the third one is the simplex method. The learning outcome that you can gain from this topic to formulate constraint optimization problems as linear program, and then to solve linear programs with graphical solution approach. And the last one is to solve constraint optimization problems using simplex method. Okay, the optimization and root location, if you can remember from topic 1, is actually related in the sense that both involve guessing and searching for a point on a function. Okay, so root location is actually searching for zeros of functions, while optimization is searching for either the minimum or maximum point. So the optimum point is where the curve is flat. Okay, in mathematical terms, this corresponds to the x value where the derivative of the function is equal to 0. In addition, the second derivative, f double prime x, indicates whether the optimum is a minimum or maximum. So if the second derivative is lesser than 0, that shows that the point is maximum. While if the second derivative is greater than 0, that is minimum point. Okay, optimization typically deals with finding the best results or finding the optimum solutions of a problem. So engineers must continuously design products or devices that can perform in an efficient way. In doing so, they are constrained by the limitations of in the physical world, and then they have to keep the cost down. Thus, they are always facing optimization problems that can balance between performance and limitations. So here are the list of some common instances that can be seen in the engineering practices dealing with optimization. Okay, among the problems that related with the civil engineering problem is like design civil engineering structures for a minimum cost, then design water resource projects like dams to mitigate flood damage while yielding maximum hydropower, predict structural behavior by minimizing potential energy, so statistical analysis and models for minimum error, maintenance planning to minimize costs, okay, and minimize waiting and idling times, especially for the construction project, and design with treatment systems to meet water quality standards at least cost. And optimization or mathematical programming problem generally can be stated as finding x, which minimize or maximize the objective function of fx subject to these two equations of inequality constraints and equality constraints. So we have equation 6.1 where the inequality constraints of dix lesser than ai, and then we have equation 6.2 where the equality constraints of eix equal to bi. So x here is n-dimensional design vector, while ai and bi are the constants. Okay, optimization problems can be classified on the basis of the form of the function. So the type of the programming here, Then we have linear programming, quadratic programming, and nonlinear programming. And then the other type of classification is based on the problem constraint. Okay, so if equation 6.1 and 6.2 here are included in the problem, so that means the problem is a constraint problem. Alright, constraint problem. While the other problems that we can see is the unconstrained and overconstrained problems. And then the last one is based on the dimensionality of the problem. So we have one dimension problem or multi-dimension problem, which is 2 or more dimension. Here the one-dimensional problems involve functions that only depend on a single dependent variable, while multi-dimensional problem involve functions that depends on 2 or more dependent variables. Okay, so now is the first subtopic in this optimization chapter, which is linear programming. Alright, linear programming is an optimization approach that deals with meeting a desired objective. This is like maximizing profit or minimizing a cost in the presence of constraints. This constraints is like a limited resources. So the term linear here implies that the mathematical functions representing both the objective and the constraints are linear, while the term programming is not mean computer programming, but rather indicate scheduling or setting an agenda. Standard form of a function. So the basic linear programming problem consists of two major parts. First is the objective function, and then the second one is the set of constraints. Okay, for the first one, for a maximization problem, the objective function can be generally expressed as maximum z equal to c1x1 plus c2x2 plus so on plus cnxn, where cj here is the payoff of each unit of the j's activity, while xj is the magnitude of the j's activity. So z is the total payoff due to the total number of activities n. The second one, which is constraints, can be represented generally as ai1 x1 plus ai2 x2 plus so on and until plus ain xn lesser than bi, where aij here is the amount of the ith resource that is consumed for each unit of the j's activity, while bi is the amount of the ith resource that is available. And then the second constraint specifies that all activities must have positive value, that is xi must greater than 0. This expresses the realistic notion that for some problems, negative activity is physically impossible. For example, we cannot produce a negative goods. So that's why the importance of the positive value of xi greater than 0. Okay, now for a better understanding on how to setting up the linear programming problem, we will look at example 1. This problem is developed from the area of chemical or petroleum engineering, but it is relevant to all areas of engineering that deal with producing products with limited resources. Okay, the question is, suppose that a gas processing plant receives a fixed amount of raw gas each week. The raw gas is processed into two grades of heating gas. First is regular and the second one is premium quality. These grades of gas are in high demand and yield different profits to the company. However, their production involves both time and on-site storage constraints. So there are two constraints, which is time and storage. For example, only one of the grades can be produced at a time, and the facility is open for only 80 hours per week. Further, there is limited on-site storage for each of the products. So this is also a constraint. All these factors are listed in the table shown here. Develop a linear programming formulation to maximize the profits of the operation. So given here is the factors, a table of factors that involved in this problem. Okay, the solution. The engineer operating this plant must decide how much of each gas to produce to maximize profits. So if the amounts of regular and premium produced weekly are designated as X1 and X2, the total weekly profit can be calculated as 151 X1 plus 175 X2. Or written as a linear programming objective function. This can be maximum Z will equal to 150 X1 plus 175 X2. The constraints can be developed in a similar fashion. For example, the raw gas used can be computed as total gas use equal to 7x1 plus 11x2. Okay, this total cannot exceed the available supply of 77 meter cube per week as stated in the table. So the constraint can be represented as 7x1 plus 11x2 mass lesser than 77 meter cube per week. And then the remaining constraints can be developed in a similar fashion. Thus, the resulting total linear programming formulation is given by maximum Z equal to 150x1 plus 175x2, which is the maximized profit. And these are subject to the constraints of 7x1 plus 11x2 lesser than 77 stated for the material constraint, and then 10x1 plus 8x2 lesser than 80 for the time constraint, x1 must lesser than 9 for the regular storage constraint, and then x2 lesser than 6 for the premium storage constraint, and x1 and x2 must greater than 0 for the positivity constraints. Note that all the set questions constitute the total LP formulation. The parenthetical explanation at the right have been appended to clarify the meaning of each term. Okay, next, let us look at the example 2 for setting up the linear programming problem. A woodworker builds and sells bands or boxes. He manufactures 2 types of boxes using a combination of 3 types of wood, which is maple, walnut, and cherry. To construct the type 1 box, the carpenter requires 2 board foot or BF of maple and 1 BF of walnut. Board foot or BF is a specialized unit of measure for the volume of lumber. It is the volume of a 1 foot length of a board 1 foot wide and 1 inch thick. To construct the type 2 box, he requires 3 board foot of cherry and 1 board foot of walnut. Given that he has 10 board foot of maple, 5 board foot of walnut, and 11 board foot of cherry, and he can sell type 1 of box for $120 and type 2 of box for $160. How many of each box type should he make to maximize his revenue? Assume that the woodworker can build the boxes in any size, therefore fractional solutions are acceptable. Okay, the solution for example 2. The decision variables in this problem are the number of type 1 and type 2 boxes to be built. Okay, they are denoted by x1 and x2 respectively. Since the goal is to maximize the revenues, and these revenues are a function of the number of boxes for each type, for each type sold, so we can represent the objective function as maximum Z equal to 120 x1 plus 160 x2. One of the constraints in this problem is availability of different types of wood. Therefore, based on the number of boxes produced, the sum of total wood requirement must be less or equal to the available amount of wood for each type. So these are the wood constraints. So the first one is 2x1 lesser than 10 for the maple constraint, 3x2 lesser than 11 for the cherry wood constraint, and the third one is x1 plus x2 lesser than 5 for the walnut type of wood constraint. In addition, there are a non-negativity constraints which ensure that our solution does not have negative number of boxes. So this is the positivity constraints, which is x1 and x2 must greater than 0. Alright, the next subtopic in this chapter is graphical solution. This is one of the method in optimization. For the graphical solution, because they are limited to 2 or 3 dimensions, okay, so the graphical solutions have very limited practical utility. However, they are very useful to demonstrate some basic concepts that underlie the general algebraic techniques used to solve higher dimensional problems with the computer. For a 2-dimensional problem, such as one in the example 1 that we discussed before, the solution space is defined as a plane with x1 measured along the abscissa and x2 along the ordinate, or x1 in the y-axis and x2 in the y-axis. And because they are linear, so the constraints can be plotted on this plane as a straight line. If the linear programming problem was formulated properly, that is, it has a solution, these constraint lines will portray a region that called as feasible solution space, okay, encompassing all possible combinations of x1 and x2 that obey the constraints. The objective function for a particular value of z can then be plotted as another straight line and superimposed in the space. Okay, the value of z can be adjusted until it is at the maximum value while still touching the feasible space. This value of z represents the optimal solution, and then the corresponding values of x1 and x2 where Z touches the feasible solution space represent the optimal values for the activities. Okay, let us look at the example 3 to clarify the method of graphical solution. Okay, the question is, develop a graphical solution for the gas processing problem previously derived in example 1. So we have the objective function of maximum Z equal to 150x1 plus 175x2. This is subject to all the constraints here. Okay, so for the first constraint is 7x1 plus 11x2 lesser than 77. The second constraint is 10x1 plus 8x2 divided by lesser than 80. And then the third constraint where x1 lesser than 9. The fourth constraint x2 lesser than 6. And the fifth and sixth constraints, which is x1 and x2 must greater than 0. So we have numbered all the constraints to identify them in the following graphical solution. Okay, for the solution, first, the constraints can be plotted on the solution space area. So shown here in the figure is the solution space. For example, the first constraint can be reformulated as a line by replacing the inequality by an equal sign and solving for x2. Okay, so x2 equal to negative 7 over 11x1 plus 7. As in figure A, the possible values of x1 and x2 that obey this constraint, which is first constraint, fall below this line. Here, the first constraint. So it falls below the arrow. The other constraints can be evaluated similarly as superimposed in figure A. So now we have the second constraint, and then third, fourth, fifth, and sixth. This is the feasible solution space. Okay, the area of A, B, C, D, E in the plot. So figure A give an additional insight that constraint 3 is redundant. Okay, this is the constraint 3. It is called redundant as the feasible solution space is unaffected if these constraints were deleted. Next, the objective function can be added to the plot. So to do this, a value of Z must be chosen. For example, here taken Z equal to 0, the objective function will become to 0 equal to 150x1 plus 175x2. Or solving this equation for x2, we derive the line as x2 equal negative 150 over 175x1. This represents a dashed line intersecting this origin. Now, since we are interested in maximizing Z, okay, we want to maximize Z, we can increase the Z to say 600, and the objective function will become this, which is x2 equal to 600 over 175 minus 150 divided by 175x1. Thus, increasing the value of the objective function moves the line away from the origin, as we can see here from the graph. But because the line is still falls within the solution space, our result here is still feasible. Okay. For the same reason, however, there is still room for improvement. Hence, Z can keep increasing until a further increase will take the objective beyond the feasible region. As shown in figure B here, the maximum value of Z corresponds to approximately 1,400, which is here. At this point, X1 is 4.9, approximately 4.9, and X2 is approximately 3.9. Thus, this graphical solution tells us that if we produce these quantities of regular and premium, we will reap a maximum profit of about 1,400. Okay, as for the conclusion, aside from determining optimal values, the graphical approach provides further insights into the problem. This can be seen by substituting the answers back into the constraints equations here. Okay, so if we substitute back the value of x1 4.9 and x2 3.9, we can get the value approximately 77 and 80 as shown here. And if we check back with this limitation, so x1 is lesser than x1, which is 4.9, lesser than 9, and x2, which is 3.9, is lesser than 6. Consequently, as is also can be seen from the plot, producing at the optimal amount of each product bring us right to the point here where we just meet the resource 1 and the time constraint 2. Okay, so such constraints are said to be binding. As is also can be seen graphically from the plot, neither of the storage constraints 3 and 4 act as limitation. Okay, these two constraints are not acting as the limitation because it's located beyond the feasible region. So such constraints, these two constraints, are called as non-binding. This leads to the practical conclusion that for this case, we can increase profit by either increasing our resource supply, which is the raw gas, or increasing our production time. And it also indicates that increasing storage would have no impact on the profit. Okay, there are 4 possible outcomes or solutions that can be generally obtained in a linear programming problems. So these are, the first one is the unique solution, which the one that we obtained from the previous example. This is where the maximum objective function intersects a single point. Okay, that is for unit solution. And then the second one is the alternate solution. So for the alternate solutions, the objective function in the example had coefficients so that it was precisely parallel to one of the constraints. So as we can see here. Right. It's parallel with the one of the constraints. Then rather than a single point, the problem would have an infinite number of optima corresponding to a line segment in figure 5a. So we have more than one point. This can be also the number. The third one is no feasible solution. So as in figure B, It is possible that the problem is set up so that there is no feasible solution. So there are no feasible region in this plot. This can be due to dealing with an unsolvable problem or due to errors in setting up the problem. And the last one is unbounded problems. As in figure C, this usually means that the problem is under constraint and therefore it has an open-ended here. As with the no feasible solution case, it can often arise from errors committed during the problem specification. Okay, now let us suppose that our problem involves a unique solution, which is the possible solution number 1 for the linear programs. The graphical approach might suggest an enumerative strategy that you need to evaluate it one by one for hunting the maximum. From the figure, it should be clear that optimum always occurs at one of the corner points where two constraints meet. So these are all the corner points when the two constraints meet. This is called as extreme point. Okay. Focusing on extreme points clearly narrows down the possible options. So we need to focus on the extreme points. Further, we can recognize that not every extreme point is feasible or satisfying all constraints. Okay, feasible here is satisfying all constraints. For example, notice that point F in the figure here is an extreme point, but it is not feasible. Okay, it's extreme point, but it's not feasible because it was beyond the feasible region. So limiting ourselves to feasible extreme points narrows the field down further. Finally, once all the feasible extreme points are identified, the one yielding the best value of the objective function represents the best solution. Okay, but finding this optimal solution could be done by exhaustively and inefficiently evaluating the value of the objective function at every extreme feasible point. So it's very tiring. Thus, the following section will discuss the simplex method, which offering a preferable strategy. Okay.